1, 2, 3, 4, 5, 6, 7. Ωραία.
Α, 1, 2. Α. Δεν το εμφανίζει. Α, να το.
πες 20 λεπτά, θα τις παραπάνω να ρωτήσεις φαντάζομαι. Αυτά είπαμε. Α, ναι.
Ναι, έχει ερωτήσεις και τα λοιπά.
Σ' άλλαξε σε εκθέσεις τώρα γιατί...
Στο Λευτέρη.
και για άλλα πράγματα.
Λευτέρη.
Ναι, πάλι ψέχνει να φας.
Λευτέρη. Θες το χειρός ή θες να παίξεις με αυτό?
Χειρός.
Δώσουμε ένα να
1, 2, 8 και 34. Okay. Well, after extending the academic quarter, let's start the second day of OSCW. Reminder that today it's the last day. You may always use the backrooms if you want to start an impromptu event, and there is the option of doing a lightning talk if you like. So with no further ado, I will invite on the stage Manolis Surligas. He is the engineer, one of the engineers behind PHASMA, our upcoming mission, doing spectrum monitoring and really interesting stuff. Manolis.
Thanks, Lefteris. Hello, everyone, again. Today I will present you the PHASMA mission, which is currently the biggest mission that we have made in Libre Space Foundation in our history. So, PHASMA is founded by the Greek ministry and is overseen by ESA. Go. Doesn't work. So the mission is, apart from 2 spacecrafts, 3 UEs. They will be in sun-synchronous orbit at around 500 kilometers, and is expected to be launched in a few days. Latest news are for 10th of November. The objective of the mission is to perform spectrum monitoring on the UHF and S-band and the GPS spectrum regions, and also increase the TRL level of the Saturn's comms. Currently, Saturn's comms is at TRL 8. It flew with Ariane 6, but we didn't manage to do a full test and full validation of the system. So, yeah. The goal of PHASMA is also to reach Saturn's comms to reach TRL 9. As said before, the project is funded by the European Union and the Greek National Recovery Fund. So the satellite itself, it's 3U and is about 3.6 kilograms. We have some COTS components, the ADCS, the battery, the APS, the solar panels, the GNSS and the S-band antennas are off the shelf. But the main powertrain of our satellite is the Saturn's comms that we use the Saturn's comms both as OBC and as the comms transceiver, because you all know that either comms or either OBC is a single point of failure. You lose one of them, you lose your mission. So we decided to reduce the complexity of the whole system and make the OBC and the comms as a single entity. The GNSS-assisted clock that we use to drive our receivers to have a reference clock and be very accurate. This is a requirement for spectrum monitoring. It's also developed by us, as well as the UHF antenna release mechanism. So all started with a FlatSat. I think that you are, or most of you are familiar with such setups. And a basic structure, like this one. And as the satellite progressed, more and more subsystem started to stack up. Yeah, this is quite nice and neat, but then you have the cabling. Yeah, it was a nightmare. But you say, okay, this is awful, but we can do better. Something better. Okay, and we can do it even better. With nice lacing and tidying up and routing things to be sure that they will not be moved during vibrations or they don't block the next assembly, which is assembly of the panels, etc. And eventually you have it. You have your satellite. Again, a lot of cables around that are traveling wildly and make your life difficult. But with a lot of effort and time and nerves and fights and and whatever, you reach a point that your satellite is almost ready for testing. So these are the two. We managed to fit everything simultaneously for testing because if you have one satellite to test. Things are not okay, but things are taking time. But imagine if you want to do that twice. So with the strict timeline that we had, it was impossible to do the testing separately. So we tried to squeeze things and do the testing simultaneously. Yeah, I think that at that point the biggest issue was how to manage cabling, routing through the TVAC chamber, handle all this information that is from the thermocouples and the various sensors that satellites have. Most of the assembly, I think the entire of the assembly took place in our clean room. Most of you saw that clean room yesterday. This was the setup with both satellites operating concurrently. We used a special suitcase that had all the interfacing with satellites, and this drastically reduced the effort and errors that could occur during traveling around to different facilities. To do the testing at various stages, TVAC, vibration, degaussing, or whatever. So this is a nice picture of Lamar. We named the satellites Lamar and Dirac from Lamar was an actress, actually, but also inventor, and she invented the frequency hopping back in World War II, if I recall correctly. Yeah, and Dirac most of you know that Dirac is a mathematician and a pioneer of actually information theory and yeah. And this is one day before going to going to the TVAC testing, the final TVAC testing of the FMs. You may have seen the famous photo of the surgeon being on the corner, exhausted. Yeah, this is Aris doing the same stuff. Yeah, the final day before the moving for the TVAC testing was, I think that was simply of 17 hours or something like this. And eventually everything went well, and we went to the Excellence facilities to deliver the satellites. In Phasma, the Phasma team has a weird sense of privacy. Here is me on my personal laptop working. With 3 different people around, seeing what I was doing. Actually, this was a very stressful situation because we identified an issue with the FPGA at the delivery. We couldn't flash the FPGA, but it was my laptop's fault, not the satellite. So everything went well. We flashed the FPGA with a different laptop. Total different story, but yeah, eventually Phasma reached the integrator of Excellence and is ready to be launched with Transporter 15 in around 15 days. So, yeah, enough with the photos. Huh? Let's go to the real stuff. As I said, we use Satellite comms as the main powertrain of our satellite. We use one for OBC and comms, and a second one as a payload to do the DSP and the spectrum monitoring. Satellite comms is an open source and open hardware project of LibreSpace, and it is co-funded also by the European Space Agency. It has 2 dedicated transceivers, one for UHF and one for S-band. And also has a co-processor, a Zynq FPGA, a 7020 for doing DSP and interesting stuff. It has an SDR on board, which a bit of limited capabilities, but fair enough for most of the CubeSat applications. The SDR works on 4 megasamples with 2 megahertz bandwidth, and we have also and on board the eMMC for storing up to 32 gigabyte of nice science data. Both the FPGA and the MCU can be configured during flight with over-the-air update software that our software team has developed. Some info about the SDR. As I said, it's up to 2 megahertz for 4 megasamples. It has user-selectable filters for wideband operation or narrowband to increase selectivity, if you like. The resolution is quite nice at 13 bits. And also we can drive our our internal clocks through a GPS assisted, for example, external clock. The analog front end, it's we spent a lot of effort to make us as good as possible the analog front end. We have a huge dynamic range with an analog AGC mechanism. And we are quite proud that with all that stuff in front, in the RF front ends, we have quite a low noise figure. It's currently it's at 1.4 dB. As I said, we use 2 Satellite comms on each Phasma. And currently, for a spectrum monitoring mission, we have huge challenges. The spectrum monitoring instantaneous bandwidth, it's quite small. It's 2 megahertz. So for Phasma, in order to cover the target frequencies, which is the whole UHF band and the whole S band, we are obliged to do sweeping. This is a compromise that, okay, a small spacecraft like CubeSats should do in order to do the spectrum monitoring, comparing to huge satellites that can have huge SDRs that and can observe instantaneously a large spectrum region. The S-band antennas are specially selected in order to have as wide as a wide response as possible, and we found some antennas that have a flat response of 150 megahertz. This is not the case for the UHF. We used simple dipoles for the UHF, so we have characterized the response of the UHF antenna, and afterwards we'll do post-processing and we'll compensate the effect of non-flat response of those antennas. So for the spectrum monitoring, the experiment has some parameters that I list them here. Notably, most of them, some key characteristics, let's say, is the FFT size, that you can select the FFT size through a telecommand. The channel distribution is how long the spectrum monitoring is performed for at a specific frequency. And some other kind of spectrum monitoring parameters, for example, the overlapping percentage. If some of you are familiar with spectrum monitoring, these are quite standard parameters. Spectrum monitoring, we cannot download the raw IQ signal on the ground station because it would be huge, and the S-band bandwidth, it's not enough to handle all this information. So we will do processing on board, and the spectrum monitoring results will be available as a heat map. So you do the FFT, then you get the power of those FFT beams, and you stack up them as a heat map. So this will be the information available actually from Phasma on the ground. Except the spectrum monitoring, we'll do also some kind of ML. Yeah, it's called, so why not? ML experiments. This is a nice activity that we have done in the past during the SDR Makerspace program. And the goal was to automatically classify different modulation schemes using machine learning. And because it has it showed a lot of potential, we said, okay, let's do this also in space. And Phasma will do that using TensorFlow Lite on board the FPGA. So yeah, let's hope for the best. So as all of our missions and projects, also Phasma is already open source and open hardware, and the same holds also for the data. So all of the data that will be produced by Phasma will be available on our Grafana infrastructure under the dashboards.sandbox.org. The Grafana dashboards are not ready yet. We have developed the first one a few days ago, but yeah, hope that we'll manage to do that at the launch. Closing my presentation, as I said, Phasma, it's an open mission, so we would like to invite anyone that has any kind of idea that may use our SDR to get in touch with us. We have the potential to reprogram the FPGA and do your experiment if you like. So yeah, if you have some cool ideas, let us know. This is our channels and where you can find us, and get in touch. Yeah, thank you.
If you have any questions.
Thank you very much. This was very interesting. Just one question. This GNS receiver, what's the precision, and is this important for the timing? And the second point, can you just explain where the need comes from to use this machine learning model for the classification of the modulation schemes? I didn't understand that.
So the GNSS is used to, we use it to tag the location of where the spectrum monitoring took place in order then to tag it and plot it on the ground. So we would like to create a heat map of the globe of the spectrum occupancy, let's say. So you need exactly where the spectrum monitoring took place. One thing. The second thing is that because we would like to also to have the, different transceivers have a slightly different frequency. Okay, so the two spacecrafts, because the mission is of two spacecraft, will have a bit of different frequency. To compensate that, we use a GPS-assisted reference clock in order for both satellites to have the exact frame frequency. So as far as the modulation classification concerns, you can train your system to identify automatically modulations. So this is an extra level of insight, let's say, after the spectrum monitoring. So spectrum monitoring gives you the idea of the spectrum occupancy and how intense it is, but classification says and potential sources or protocols that occupy the spectrum.
I remember another project called ElectroSense, which was also doing a spectrum classification. So they delivered an image on the Raspberry Pi, and also they had a hardware and software-defined radio, which was also sweeping the spectrum. And they were also, let's say, collecting the data locally. And what I think is maybe this data is available to check, or maybe, I don't know. That's why I mention it, okay?
Yeah, and the bigger issue I think that we try to solve is, I don't know how many of you have made a space mission, but in our case, we would like to know, okay, which is the noise characteristics of the band that I'm gonna use. This information is not available. So you fly a mission, you do spreadsheets with link budgets, with whatever, and you don't know the noise floor there, or the occupancy. Will be the noise high? Will be the noise low? Should I use a filter because on nearby I have potential interference? What should I do? And this was let's say, the main driving force of doing such a mission. And as I said, this information will be available. So imagine the power of such a mission for the whole community.
Thanks for the presentation. Maybe I missed in the beginning. What is the planned lifetime of this mission?
Currently, the drama simulation says that should be 5 years.
And the 3 satellites, identical satellites, will they be flying in whatever configuration, or?
Currently, we fly 2. Initially, the plan was 3. We are flying 2, but we are searching for a fund to fly the 3rd one, because we already have the 3rd one, but it's on our lab.
Okay, maybe I kind of missed it in the beginning. And what kind of orbit they are, and do you have any kind of thrusters to keep their orbit?
Yeah, it's a sun-synchronous orbit at 500 kilometers.
And they keep it for 5 years without any thrusters?
No active thrusting. No, we do have only the ADCS to maneuver the satellite, pointing the antennas, the S-band antennas towards Earth.
Thank you.
So we don't have time for more questions.
Thank you.
Anyone else?
Okay. Oh, that was nice. So we are preparing for the next slide. I may invite our colleagues, Konstantinos from CubeSat, to give a presentation about their satellite. It's CubeSat is a satellite from the Aristotle University of Athens, Thessaloniki, and
so they're joining online.
they're joining online.
Yeah.
Okay.
We need the systems engineer for this, and I come back after the talk ends to continue with in the next talk.
Okay. The issue here is that our colleague had an issue attending due to medical reasons, and they will be joining us online to facilitate the talk.
Okay, so can you hear me?
Yes, we can.
Okay, perfect. So yeah, I was not supposed to do this presentation as well, but our colleague had a medical emergency, so I'm doing this. But we would like also to thank you for letting us arranging this to be able to do this online. So we'll start. It has been a lot of years since we have been in this workshop as well, presenting our satellite. And this is kind of a status update on the progress that we've made so far. So this is SpaceDot. SpaceDot is a multidisciplinary university team in the Aristotle University of Thessaloniki. And it has more than 20 members, and our goals are to launch satellites and to cultivate space engineering in Greece. We make everything with our open source philosophy, so all our designs and our testing reports and everything are open in our GitLab, and you can find everything there. We will go through basically our mission and what our progress has been so far. So our first satellite, and the one that we're planning to talk about today, is a CubeSat. And what's the mission of a CubeSat? It's a biological mission. So we're planning to study cells in orbit. And we're planning to do this by launching basically a small lab that is hosted inside the 3-unit CubeSat. And that we will study cells that are very similar to human cells, and study the effects of microgravity and the radiation environment on them in a larger scale that it has been done ever before. We do this with ESA support, and basically we are under the Flyer satellite program from ESA, and since 2020. And now I will present a bit more details regarding our satellite and how it looks like and the inside. So this is a CubeSat, and it has both in-house subsystems and COTS subsystems. The in-house subsystems are 3, and the first one is our ComSport, which is based on the LSF SatMox ComSport with some modifications to facilitate our design. So we do the full environmental qualification and everything again. The second one is the OBC DCS board, which is basically a PCB that hosts the onboard computer and the attitude and the determination control of a subsystem. So this subsystem is also in-house, including all the algorithms and everything that we will use in orbit. And the third subsystem that is in-house and that we are designing from scratch is the whole payload. And this is basically the two units that you can see in the middle. This is a container that hosts everything. So basically the mini lab that I mentioned before. And the rest of the subsystems are codes, so we're buying them from commercial companies. And in order to take a closer look inside the payload to understand a bit what the mission is and how it works. So the heart of the payload is basically a lab on a chip. This is a microfluidic technology that we're using, which basically hosts all the cells that we're planning to study. And this is supported by a complex fluidic system, including pumps and valves. And everything is controlled by our SU-PCB, which is another in-house PCB that we designed. And it basically controls all the fluidics, the imaging system, and also the thermal control that we're using inside the payload. And in order to understand a bit what the scientific output of the mission is and what we're planning to study eventually, we're planning to study how much the cells grow in space. So basically, this is the image that we're getting from our payload, and that is transmitted to our ground station. Basically, this is what we're planning to study. So you can see on the right in this video how the cells grow and how it looks like in the microscope. And yeah, this will tell us everything about what we need to know about these cells. So, and what's our progress so far regarding environmental testing and our in-house subsystems? So basically, so far we have qualified everything for vibrations. So all three of our in-house subsystems have been tested in ESA facilities successfully, and they are basically ready to be launched. Since we also passed all the TIVA qualification testing, actually 2 weeks ago, we successfully passed the TIVA testing for our payload, which was a full 2-week test in order to perform all the experiments and verify that everything works in order to be able to do our experiments in orbit. And regarding our timeline, so as I mentioned before, we have been here in this workshop some years ago. So back then, we had just been accepted to the Fly Your Satellite program. So since then, we have been doing quite a lot of things. So our first milestone was passing the critical design review, which is basically when we submitted all the documentation to ESA and it passed all the reviews, and basically the design was closed, and we proceeded to do all the manufacturing and testing of our subsystems. And then the next milestones were the qualification of the communications board first, and then the OBC DCS board and the payload, leading us to now, when now we're planning to procure all the rest of the subsystems and proceed with the integration testing and system level testing. Thankfully, and if everything goes as planned, next year we might be able to present our system level testing results. And then a CubeSat will be in orbit as planned in 2027. And the experiments will last 2 years approximately. So there will be 3 experiments in orbit. 3 times we will study a different part of the chip basically. And we will do the same control experiment on Earth to be able to compare the results. And in this presentation, we wanted to share a bit of some fun facts that led us to basically some good practices that we are applying to all our AAV activities. And yeah, so I hope you enjoy them, and they can also be applied to, I think, most of CubeSat missions and complex assemblies that NN is doing. So the first thing that we did, it was to define all the assembly procedures by a lot of mockups and a lot of printed parts. So yeah, first iterations always are very hard, but every time when you define the length of the cables and you define more all the distances and the tolerances, then everything becomes easier. So this is how we started. The picture on the left. So this was one of the first samples of the payload in order to basically end up to the image on the right, which also passed the vibration testing. And yeah, Captain is your best friend. So we ended up securing everything because, as you can see, there is a lot of cables and a lot of tubes as well, which are filled with fluid. So yeah, we used a lot of Kaplan to secure everything in place and to be able to not stretch anything, to not have any leaks. And this worked quite well since we passed successfully all the vibrations. So yeah, that's a good thing that we learned through testing. So for the cables, we had to procure a lot of cables during this process, and there are a lot of different conventions for even very similar connectors and cables. So yeah, everything is important to follow the conventions, to triple check everything, to continuity check everything, and to have a clean setup. So you can see on the left what everyone should do and what you shouldn't do. And you can see that on the bottom image, you cannot see which cable goes where, but on the image on the top, everything is clean. And one more rule that we applied on every clean room visit and every AIV activity that we did, especially with EQM and FM parts, was that we always have two persons inside the clean room and handling equipment. One of them is doing the product assurance, basically keeping everything, noting everything down, and in very important activities, we also take videos of everything and make sure that we can go back to what we did and verify that everything was done correctly. So this is a bit of a fun thing that happened during one of our clean room activities. So it's very important to know that the CAD is different than real life, and always fit check everything once they arrive. Although especially when you have machined parts and complex assemblies. So for this, you can see that this pump, this is the black and metal thing on the top. This was fitting nicely in the CAD, but you can see that in the assembly, eventually, it did not fit well. And this was not because of a bad design or anything, because after a while, after a bit of troubleshooting, we noticed that on the pump, there is the sticker of the pump, which basically did not look like a sticker, and it was almost invisible to see. But stickers are three-dimensional, and this was causing this problem. So when we removed it, the pump was fitting nicely. It was a perfect fit. So yeah, stickers are three-dimensional, and they also have material properties. So remove everything that is not supposed to be there before the final assembly. And now I want to share a bit of our contributions to the open source community. As I said before, everything is open in our design. So yeah, on the hardware side, everything for our payload, the whole platform, the whole lab is basically open in our GitLab. So yeah, anyone can replicate it and build their own mini lab to send to space if they want to. Our OBC DCS board is also open, all the design files and all the testing that we did. Our flatsat, which is not procured yet, but we're planning to procure it soon and start integrating our subsystems, hopefully very soon. And a lot of test adapters that we made for different shakers and for the TVAC, for example, that are compatible with PC104 standard PCBs. So they can also be used for testing of different boards if needed. And some analysis things that we did after design. So basically, we started working on the link budget again, and we tried to do it a modular script, basically to integrate it with HFSS and SDK to be able to use it in different and various scenarios. And we also did again the radiation analysis in order to see the effect of radiation on the cells and be able to prepare in a better way for our radiation testing that we're planning to do soon. We performed the thermal analysis with Isaton And everything, all our models and everything is open in our GitLab. And this goes to both simulate the test and also simulate the conditions in orbit for our mission. And since the new regulations regarding the orbiting should be respected, we also performed again our SDMR analysis with Rama, and everything also is open in our GitLab, so you can also take a look if you want, since this has to be applied now to all the missions. And yeah, some very random open source things regarding software and also cables. So you can take a look in these as well. And we have open all our ADCS software and all the simulations that we did for the in-orbit implementation of the algorithms. And we are now working more on the embedded part of the ADCS. And also the implementation of the ECSS services for our onboard software is also open in our GitLab. And of course, all the documentation on not only our design, but also test reports that we did during our testing and manufacturing phase. So yeah, this is everything. So since everything is open source, of course, we are always open to new ideas, and feel free to go to our GitLab and take a look and let us know if you have any proposals or any ideas. It's always welcome from us. And if you want to read more about our team, this is you can scan this QR code or send us an email, of course. I think that's it from my side. So I think I forgot to introduce. So I'm Christina. I'm the system engineer of the team right now. And you will hear more about communications and our status there from Konstantinos and Diana in the presentation after this. So if you have any questions.
Thank you so much. We do have time for questions. There's a question already.
Yes.
Hello. Hi. So,
Hi.
yeah, actually, I have one question for you, but first I want to actually thank you for open sourcing your implementation of the PUS standard. We actually also use it for our project, so yeah, we already made use of your work there. And my question is, what is your experience working with YAMS, this mission control software that you also use?
Yes, so I think Anastasis is also in the call and has worked on this as well, so he can also say a bit more. But so far we have used it basically to implement some basic TMTC, and during our test campaigns, basically the first test campaigns, to communicate with the device under test.
But yeah, do you like it? Is there something that could be better? Yeah, what is your general feel about YAMS?
So I have not personally used it, so I cannot say that I like it or not. But yeah, Anastasis, if you want to jump in, you can.
Hello. Just can you say something about the biological experiments and why they behave differently in space than on Earth?
You mean what the effect would be? The effect would be on the cells, basically, and on their growth.
Yes. To what is it? It's because of weightlessness, or is it because of, I don't know, some other condition that they are expected to behave differently in space than on Earth?
So basically, this is the two conditions that we want to study are radiation and microgravity. Of course, we can say that there are a lot of space conditions like thermal conditions that vary, etc. But we are trying to mitigate this. So this is why we have all the cells in the container that is pressurized. So we have 1 atmosphere, which is like in Earth, and we also have thermal control. So the two conditions that we're planning to study are radiation and also microgravity. And we want to study the gene expression, basically, of the cells. And we study this with monitoring the growth of the cells, so the growth rate of the cells. And we want to see if this changes due to microgravity and radiation. And we're planning also to do some radiation tests in next month in order to see how the cells are affected from radiation, and in order to be able to also compare with the effects in space.
Okay, it seems that we don't have any other questions. Thank you so much for managing to speak to us online. All the best to your
Thanks a lot
colleagues.
for arranging this.
So there is a scheduled family photo. Anyone not willing to participate, they are, well, they're okay to do so. And we're gonna go out, get our family photo, and then have a break for coffee and tea. We will be back at 12, local.
παρουσιάσεις το άλλο το πεδίο. Οκ. Ωραία. Έτσι να αλλάξω τα presentations. Αυτό είναι έξυπνο, κλείνει μόνο του το τέτοιο. Αλλά πρέπει να το κάνεις off-on. Αυτό πριν δεν δούλευε στο Μανώλη.
Πρέπει να τους δίνουμε έτσι να είναι στην τάξη. Μπορώ να μας πει την οθόνη να έχει οδηγίες σε πώς θα πω στο δικό μου.
Εντάξει,
500 λέξεις. Μισό λεπτό να δω. Ευχαριστούμε που επιλέξετε.
Εδώ, ένα τέτοιο που θα γράφει οδηγίες. Να είσαι σε αυτή την απόσταση από το μικρόφωνο.
Ναι, καλά.
Μπορείς να κάνεις μισό βήμα δεξιά, μισό βήμα αριστερά. Απαγορεύεται το μπρος πίσω.
Εγώ λέω να είμαι ο δεύτερος ομιλητής που θα είμαι εδώ. Δεν θα έχω ασύ, δεν θέλω να πω.
Όχι, για πατά το βελάκι του δεξί.
Βολικός. Βολικός.
Πολύ τι.
Βολικός, λέω. Βολικός.
Εγώ ήμουν ο χειρότερος. Ναι, αφού έκανα. Το καταλάβαινε, κάποια στιγμή το καταλάβαινε, το έφερνα πιο κοντά, άκουγα πιο δυνατά, λέω καλά πήγαινε λίγο. Τίποτα, χιλόφωνα μόνο.
Είναι βολικά, απλά έχουν το θέμα που όταν χιλόφωνα τις σφυρίζουν πάρα πολύ, επειδή είναι όμοιλοι.
Ναι.
Είναι παντοκατευθυντικά. Για να πω.
Δεν τα έχεις όμως πάνω σου
δεν παίζει ρόλο. Ουσιαστικά το CubeSat είναι όμοιλοι, δηλαδή πιάνει από παντού. Είναι έτσι γιατί πολύ την ώρα της παράστασης όλες μπορεί να το βάλει εδώ, μπορεί να το βάλει εδώ, μπορεί να το βάλει εδώ.
Κατάλαβα, ναι.
Και
Οπότε δεν μπορείς να έχεις.
Αν δεν είναι όμνη, δεν μπορείς να το βάλεις κατευθείαν γιατί θα το ακούει. Οπότε επειδή είναι όμνη, αρπάζει απίστευτο. Δηλαδή θέλει να κάτσεις στο Samsung και να κάνεις δουλειά, να κάτσεις να κάνεις μόνο το ελληνικό, ό,τι συχνότητα αρπάζει. Θέλει 3-4 δηλαδή σίγουρα.
Εμένα με νοιάζει λίγο, να με βολεύει περισσότερο για να έχω κάτι να κάνω τα χέρια μου με το μικρόφωνο.
Ναι.
Το ένα στην τσέπη, το άλλο.
Ναι, για να μην
Το μικρόφωνο πέτου παίζει για live.
Δεν χρησιμοποιείται ιδιαίτερα. Όχι. Περισσότερο νομίζω παίζει για τύπου συνεντεύξεις. Τώρα σε τέτοια επίπεδο που δεν συνέδρευαν ποτέ, ούτε σε live ποτέ. Δηλαδή
χιλόφωνο. Τα χιλόφωνα.
Πέτου.
Πέτου.
Χιλόφωνο παίζει στη συνέντευξη. Και χιλόφωνο.
Πέτου. Έχει συνήθως πολύ θόρυβο και άμα κουνιέσαι και όλα παίζει να τρίβεται, να κάνει. Παίζει να είναι από τα χειρότερα.
Έτσι δεν είναι παίζει να κατακούσουμε. Είναι καλή φάση.
Τι είναι?
Αυτά που είναι πάνω στο πόντιο που είναι το μακρολόγο.
Ναι.
Που είναι σε συνέδραση, σε δελτία τύπου.
Σε meeting rooms.
Ναι. Αυτό είναι πολύ.
Πώς μόνο αυτό βάλω κάπου σταθερά. Γιατί είναι δίδυ. Ναι.
Έχει το βάρος.
Έχει, αφού είναι.
Τους δίσκους μέσα από αυτό.
Cool. Ωραία. Είναι ο Φρέντι. Το κινητός εδώ είναι.
Have a clicker? Oh, the forward. Just remember to open it.
Άνοιξε. Okay, so as we wait for people to come, yes. So the next talk is about the census ground station. It's by Chiara. From the Observatoire de Paris, and she will give all the details herself because she knows better about her work.
Thank you. Hello, so hi everyone. I'm Chiara, I work at Paris Observatory as a ground system engineer, and I'm going to present the project we're working on the census ground station as a node in nanosat grid. Not really working. Okay, so I'm going to give a quick overview of of census. Then I'm going to no. I don't know what. Okay, I will just go like this. I'm going to talk about our ground station, and then I'm going to present the nanosat grid project. So Census is the space pole of PSL University. Yes, it's an expertise pole for the scientific new space, meaning that we act as a project incubator, helping scientists to develop their mission, the space mission, from an engineering point of view. We support them with the development cycle of their mission, and in general, we provide expertise in all new space-related topics, and we serve as a learning environment for students, so with the internship and projects and everything. And this is our small, nice ground station. We have a UHF and a VHF antenna, the two rotators, and the cabinet with all the electronic components. And we operate the station in essentially two modes. The first one is the SatNOX mode, in which the station is just basically connected to the SatNOX network. And we are online since almost 6 years now. Currently, we have only the VHF antenna because we're waiting on some components for the UHF that are missing, but soon there will be both. And yes, what I wanted to talk about is how we install the client. We use the Ansible playbook, and we run the playbook inside a Docker container. So to exploit at most the Docker possibility, the Docker tool, we created two custom Docker images. The first one is run on the main computer in the office. and it creates the installer container, while the second one is a target image and is run on the target computer, in our case the one on the GS, on the ground station, and it creates the target container, and then the installer container runs the playbook in the target container. So this is done in a fully automated way, so it really helps in reproducibility and portability of the projects, because there are many different buildings and many people working with the ground station that are not used to do that, so they're not really into SatNox, they don't know really well how it works. So it allows to install the client remotely with the 3 options, so to reinstall it from scratch, to reconfigure all the parameters of the SatNox setup, or to restart from the previous stable setup, or to save the current configuration as the stable one. So that's the configuration used by option number 2. And then the other operating mode is the census mode, in which we are planning to allow the operation of satellites from the observatory, independently from SatNox network. So what we are, the major feature we have to implement is transmission. And we are trying to design this mode in a way to make it very flexible and adaptable to different future missions. So from the hardware point of view, we only have to install the transceiver, which we are now currently testing because it's it's a bit old. And yeah, the rest of the hardware will mainly remain the same. Whereas from the software point of view, we're planning to use open source software for reception, so gpredict, hamlib for tracking, GQRX, and new radio for signal processing. Whereas for transmission, we are trying to create a versatile and adaptable tool for generation of telecommands. And that's what we're trying to work, that's the plan. Then for the signal processing and tracking, we'll always use the open source softwares. And all these efforts will serve as a base to integrate our station in the Nanosat Grid network, which is a project we're working on, where we plan to, much like SatNox, but restricted to research and technology institution, and in which we are allowed to transmit also to nanosatellite. And this will, of course, bring several benefits to the R&T community, in particular increasing redundancy and reliability of operation, which is a main driver for the project, why we created it, and to increase the geographical and spectral coverage, the R&T sovereignty, and to optimize the usage of resources. So given this large objective, we are trying, we derive the main needs for the project. So Nanosat Grid shall grant sovereignty of R&T operation through the integration of a partner station into a network. And it shall allow the operations of R&T nanosatellites from any station in the network, remaining scalable and flexible, meaning that we would like to allow to have possible interfaces with SatNox, and in particular with the SatNox orchestrator. And this is the basic idea of the architecture. So the main user interface will be an API gateway that will route the request to the proper software component. We will have a global orchestrator to deal with the booking and scheduling, a centralized controller to establish links between the nodes of the network and to actually allow the data exchange. And the centralized controller will talk to the local orchestrator, that is the software installed locally at each lab, and it will control the local hardware. Then we plan to have 3 databases for the moment, one for the ground stations, one for the satellites, and one for the network data, mainly for performance tracking and everything. And as an example, for uplinking, the user will upload a telecommand file to the API gateway that will route the request to the centralized controller. The centralized controller will perform a first processing, so encoding the telecommand, if that's possible for privacy reasons of partners and everything, and it will route it to the laboratory tasked with uplinking, in this case LabN. And the local orchestrator will receive the request and command the hardware and send the signal. So yeah, this is it. So what we are trying to do is to put some effort in improving our ground station to become part of this nanosat grid and to actually build this nanosat grid. And next things we will practically do are like to finalize the uplink chain of census mode and to develop and test the first proof of concept for the project. So we have some partners that will allow us to try to actually send a telecommand from a different ground station. So that's basically it. And if you have any idea, recommendation, or anything, please let me know.
Hello, thank you for the presentation. I was wondering, you seem to have only one level of hierarchy with the global orchestrator, and then you have the local ones. And I was wondering why you chose that instead of a, let's say, more distributed hierarchy where the global orchestrator manages let's say, regional orchestrators and so forth. I'm drawing inspiration from global load balancing, which kind of does something similar, but it adds more levels of hierarchy. And then my second question would be, have you considered that you're maybe trying to be too future-proof and it costs in development time? Because it's a trade-off, and I was wondering why you made the choice you made.
So yes, the project is at a very early stage. So we're still developing the actual system architecture. This was the first idea, and for the moment we're trying to go with that. But of course we will explore alternatives. And yes, the main concern is actually the budget, because we're a public institution and we're looking for partners to support the project. So the timing will depend a lot on it, I would say. Okay, thank you. Thank you very much.
Thank you, Chiara. Next in line is our esteemed colleague, Victoria. She's going to talk about mission control software and fun stuff with Yanks.
Thank you, Elkos. It's actually YAMS. Everything says it wrong, so I'm going to correct that here. Like as Elkos said, I'm Victoria. I'm from LibreSpace Foundation, and today I'm going to present you how to design a mission control center using only open source tools. So, in case you do not already know, we are the LibreSpace Foundation, and we create open source technologies for space. So, how actually this all began and a little bit about history. In our earlier missions, we used to use protobuf messages to define our mission database. So the mission database is basically how you encode the telemetry and the telecommands. And we had designed a custom CLI tool for the mission control software. This was functional. Here you can see this is a proto file that has a radio statistics message defined, and this is actually a screenshot from the CLI tool. You can see that it's functional. It has the tap feature, but it was very limited. So as the mission scaled up, this had begun to be getting a problem. So what was the challenge actually? Since we were developing our own in-house onboard computer and telecommunications board, the Sednex comms, as was mentioned in previous presentations, and as missions grew more complex and more frequent, we needed an abstraction layer that could be scaled across missions. And maintaining our own mission control was very painful and not fun. And you had to do everything manually. And we were searching for something ready, standard, and hopefully open. So that's when we discovered YAMS. YAMS is an open source software framework for telemetry and control of spacecrafts, payloads, and ground stations. It provided us with everything we were searching for. It provided us with an API that an operator could use. It gave us alarm generations. It gave us command history, real-time plots, command acknowledgements, dashboards, timelines, and one of the most important things, it had built-in support for space industry standards, like for the CCSDS CFDP, which is the file delivery protocol, and the CCSDS XTC, which is how you define your database in space. It was very modular, and you could create your own preprocessors and plugins easily in Java and Rust, which we didn't like very much, but whatever. And it actually has a very active community and forum. They reply like within a day, which is nice. Well, my icons didn't format well, but yeah, whatever. Yeah, this is actually we initially had the protobuf that we used for the mission database, and then we chose the XTC. Why we did that? Because the XTC is a little bit more complicated to do, so we did it, both of them provide the data structure, but the protobuf is very limited. It doesn't contain any information about units, calibrations, alarms, limits, like what an operator could send to the system without breaking it, validity conditions that would trigger the alarms. It has like many stuff, engineering transformations from raw values to engineering values. You can define like complete algorithms inside the XTC. And it's actually the space standard. It stands for the standard that it's used. And yeah. And why this matters? It matters because in space, standards are very crucial. So when you work with external partners, you cannot actually afford to have ad hoc implementations because you would need to redesign your system for every collaboration, and also YAMS supports XTC natively, so you just code your file with a mission database, upload it, and everything works just fine. This is an example of how you would define a command in an XML file. the XML file. Basically, the XTC is the schema that you would use for an XML file, and for your database, it's all you need, just an XML file. It looks a little bit scary, but it's not. It has a learning curve that you need to follow to understand it, but after that, it's just easy, and it's very powerful. You can support everything and scale your mission up, and it's great. So something else, on top of your space package, besides the way how you define the messages, you have something else that it's very important. You have your headers that we implemented in YAMS. And this is the header for the space package, where this thing we added recently, and it was essential. Because this is this field here, the spacecraft ID, is actually how we differentiate between our payloads. We have a mission, as my colleague said, the PHASMA mission, and it has we actually have 2 satellites, and they transmit on the same frequency. So you need a way to differentiate between the satellites. And this header here just says which satellite is going to transmit the telemetry or get the telecommand. So after that comes another header, which is the CCSDS header that has some metadata about the package. And it contains like the packet type, if it's telemetry or telecommand. It's something that YAMS would parse, and automatically you need to add that you can like not use the SLP, but this thing you have to add, otherwise YAMS won't work. So you would need to like define stuff like the packet type, so YAMS could route that, like sequence flags, like is this your first packet, your second one, and the packet data length. So, and a little bit about the whole architecture. So we have on our, our onboard computer is also a transceiver, and we have a few links that we can use. We have dual band RF links, like we have S-band and UHF. And we also have CAN bus for testing or communicating if it works as a payload with the onboard computer. So, you basically, in order to send telecommand, you have to I will talk about data links later, but you actually can use the physical interface, for example, S-band. SDR, an SDR will decode it, modulate it, and send it to gateway with a 0MQ protocol. And the gateway is a custom tool that we actually designed that would forward. It's basically just a forwarder, but would forward it to a UDP port that a YAMS server can subscribe to. And the YAMS server then will forward it to the API, or I also added the robot framework here, which is something that we use for testing, and I will come back to that later. And yeah, everything is each link works basically the same, so you can use either RF or a kind of D-link, and you will have the same telecommands and telemetries in YAMS. So, as I said about the data links are basically how you would discriminate between the telemetries and the telecommands. It's something that's needed to be defined for multiple spacecrafts. And here's how you would define a data link in YAMS. It would have a specific spacecraft ID to define your spacecraft, and you would have to add different data links for different telecommands based on if it's the S-band, the UHF, or the kind of D-link. And yeah, for some of that, you would have to develop your own post-processors, like we did for the USLP frame parsing, and you can actually just get that from our GitLab if you want to implement it yourself. So this is how the web API looks, and on the first page you can see the links. You can see the DRAC and the Lamar satellite spacecraft here. You have the status here that you can monitor. You can monitor the packages that everything was received correctly. Yeah, and okay, how would an operator send a telecommand? It's actually really easy. The interface is very nice, so you just go to the menu here, select one of the telecommands, or just type it because they are far too many. You have telecommands for the core functionality of the board. You have mission-specific telecommands, so you select one of those, and you just, there's a nice thing that you can select from, and you would have to specify your link, like from where do you want it to be sent from, for what satellite, for the Lamar, for the Dirac, via UHF or S-band, or CAN for the testing. And this is how you will receive, like here, you can see the telemetry packets that the operations center has received. So in chronological order here, you can see the links and the generation time. Here you can see a packet with the health telemetry, the temperatures here, and all the values to monitor your spacecraft. And yeah, last but not least, YAMS isn't only our mission control, used for our mission control, it's also a part of our fully automated test and validation suite. So basically what we did is we connected Robot Framework. Robot Framework is a very powerful tool for testing. We connected it directly to the YAMS server. It's Python API, and we can now send commands automatically, monitor telemetries in real time, and run end-to-end test scenarios covering full system functionality, and all tests run autonomously. So previously we had to manually press buttons, and now we just send a command and go have a cup of coffee, and in a couple of hours everything is tested. Here you can see a test report generated for the over-the-air update, and it's basically done automatically by the Robot Framework. And you can see that 78 tests passed and none of that failed. But if it fails, you can debug each. You can see the values inside. It's very, very powerful and not that hard to implement. And yeah, last but not least, this is our Mission Control Center. We, as my colleague Manoli said, have a launch coming up, and we are very excited about that, so wish us luck. This is our first big, so complicated mission that we will use YAMS in. And yeah, I hope, fingers crossed, it will go well. And okay, so thank you for your attention, and if you want to learn more, you can visit our GitLab page. You can find us on Matrix, or just email us. Thank you very much.
Any questions?
Sorry, I forgot about the questions.
Hello, thank you for the presentation. So, quick question. You mentioned you shifted to a robot-based testing automation approach. I was wondering, do you still do manual testing as a safety precaution?
Actually, no. It's completely safe to run it, and it actually identifies all the errors that could go wrong. It saved us a lot of development time. Well, of course, if something fails, you go to and do it manually and see what fails, but you have all your subsystems that you actually do that if something fails.
So, coming from a testing background as well, because you're working on something that is mission critical, there is a risk in choosing to automate everything, because sometimes the machine will follow predefined scenarios, whereas a human doing exploratory testing, for example, can catch things that you did not expect. And I'm guessing a failure of an unexpected, let's say, thing happening would be catastrophic, correct?
Okay, we try to, of course, capture everything. In the development phase, we try to identify all the edge corner cases. And after that, if you will run your test, of course, you will run the firmware and you would see if it runs. But the robot framework provides you with more insight, because you cannot test, it's very complex, you cannot test all the systems. If something fails, it will like trigger you go there and find that. And I think it's an addition rather than an inconvenience to the process. It gives you more.
Testing, sorry. To repeat for the stream, exploratory testing is definitely something you do on top of automated testing, because, as you said, the human cannot perform all the testing. It's just that when you have to do with things that are mission critical or sensitive to failure, you usually avoid relying on automated testing 100%. It's something you said that
Yeah, it's actually quite impossible, because you have a lot of systems that you need to have your checks. So it's possible. Like this, I showed you, it were 78 tests only for one functionality of the board. So you cannot capture everything, and it does essentially what a human would do. It just does it quickly and automatically. You would send these commands manually, you would see the result. So it's just like a very fast human doing that.
Okay, thank you, Vic.
Yeah. Now, Ioana and Konstantinos from SpaceDot, the CubeSat team of the University of the Aristotle University of Thessaloniki, are going to present their work of communicating with a CubeSat via SatNOX-based platform. They're students, so they got the stage.
Thank you very much. So, I'm Konstantinos. We saw earlier our biological experiment, our nanosatellite CubeSat. And let's follow our image data acquired from our camera and follow them through our communication subsystem all the way out the antenna and downlinked into our ground station. Wait a minute. That's our previous presentation, I think. Right? Yeah.
Give me 5 minutes.
Okay, perfect. Okay, so I guess we can start now with the communication subsystem. Yeah, we're using S-band patch antenna operating at 2.4 gigahertz for downlinking our image data. Directional antenna, that's why we have our ADCS to support us. And of course, UHF turnstile to receive our telemetry and send our telecommands. This is our PCB comms based on Satnox LSF design. A little bit modified, but yeah, we can see our FPGA, MCU, and our EMI shield here. And this is our ground station antennas. This is for the S-band, and the helical one here. So yeah, that's the ground station. Ioanna will show us a few things later on how the GNU radio works. This is a basic functional graph. And of course, we're using the YAMLs mentioned already for our mission control software. So yeah, we need our FPGA here to perform our critical digital signal processing tasks. We need parallelism and pipelining here. And also we have the reconfigurable path in orbit option using this. Whatever we discuss here, all are open source. You can take it afterwards. We're using and we're working using Vivado VTs with a very low hardware descriptive language. And yeah, that's the mess going on in orbit in the CubeSat. And here is the data path from DMA, acquiring our data, all the way through our LVDS interface. We're gonna loop through this one by one. So we have our image acquired using SPI from the rest of the satellite, stored in our ARAM FPGA, and then we pass it into our LDPC core, designed from a member of our team. And we get our data encoded and ready for the modulation, which is what we'll explore today. Our OQPSK modulator, as it is recommended to use for its high efficiency and robustness by the CCSDS protocols. That's our overview here. We have two finite state machines to control the main operations. And the internal data path, starting from the valid data, here, where the separation is done. We have the bitstream of the image, split it into two I and Q components, and then translate it into their amplitudes by our master data handler. That's the easy part, yes, because then we have our FSMs for the rest of the logic, the flags, and the implementation of our time delay over a half-period symbol, which is done as we keep our I and Q component in a different state. We have the send state and the offset state to ensure that when we're sending the I, the Q is idle. And yeah, we have for the final digital signal processing states, our RRC filter to avoid this messy received constellation and get this beautiful thing Ioanna will show us next. And this is the final stage when we're driving our encoded, modulated, and filtered data inside our transceiver using a higher clock domain to drive our LVDS interface and get our antenna transmitting. That's pretty much a high-level overview of our OQPSK encoder and FPGA implementation of our S-band chain. And we're going with Ioanna through our ground station.
So hello from me too. So we talked about the journey of our signal, our data in the physical layer. So now let's go to the ground station. So we have the electromagnetic wave, which is coming to our antennas. And this is a block diagram of the ground station. Since we are talking about the OQPSK demodulation, we will be using the S-band route to demodulate and filter everything that we get. So we see that we have an LNA, we have a filter, we have an RF switch, then we go through the SDR, and finally our PC. In the PC, we use the GNU Radio, which is an open source tool that helps us with our signal processing because it has a very easy way to help us actually implement the demodulation through using blocks. What we do with the GNU Radio is that we implement the frequency and phase lock, the error correction, channel coding, and the Doppler compensation for very obvious reasons. So Doppler compensation, we get a TLE file, and assuming actually, and from the TLE file, we get data about the location of the satellite, and therefore we can calculate the frequency offset. Then, of course, we insert this frequency offset in the channel model in order to compensate for that. And because, of course, the channel inserts some noise too, we add the Costas loop to compensate for the added noise too. And here is the constellation that we get after the first Costas loop of the flow graph. This is our OQPSK modulation and demodulation scheme in GNU Radio, as I said before. We can see that we also have a modulation here that we created in GNU Radio for simulation reasons, because, of course, as we said before, the modulation will happen in the physical layer. So we will focus on the middle part. Here we have a pole-phase clock sync that we use it to synchronize our I and Q components, and in order to maximize the signal-to-noise ratio and minimize the inter-symbol interference. Also, I have to say that we have actually based our implementation in the GNU Radio's OQPSK demodulation, QPSK demodulation. So therefore, we placed the linear equalizer after our sync, and it worked, so we kept it. But of course, the equalizer inserts some noise too, so in order to compensate for that, we added a second Costas loop, because we had observed that it actually created a rotation in our constellation. So this is our final constellation. We can see the decision areas very clearly, and we like that. So after that, we have to continue with the mapping. We finalized the constellation, so we transferred the clean constellation points into binary data, and then we measure bit error rate performance by obtaining the synchronized and complex symbols that we get from the constellation. Then we map them back into bits, and then we finally compare them to the transmitted ones. So what are our next steps? We have to verify the IP cores that we have presented. We are much awaiting for the finalization of the GMSK, RX, and TX chain. We have to perform end-to-end testing for both our antennas, the UHF and the S-band. And finally, we have to integrate our comms board with the rest of the in-house CubeSat systems, like the OBC, the antennas, the payload, in the flat-sat mode. So that's all from us. Thank you for your attention. You can read more about us in those links. You can scan the QR. And thank you.
It seemed easier in the presentation, I have to say. So, as we're a lot of comms people here, electronics ones, and I have to say I'm very happy to meet you all after the presentation to discuss some major blocking points and some issues we have. So yes, thank you, and we're open to whatever questions you have.
Great work, thanks. So a question from my side. You mentioned about the QPSK transmission. This is, as far as I saw from the flow graph, at the current time, it's a continuous stream, right? So you don't have a preamble or any kind of framing right now, correct?
Yeah, basically, we have a
So
continuous
you have
stream.
random bits through your QPSK on the FPGA, and then you do the modulation and just transmit them over the air.
We don't have that yet. We have just, you're talking about the GNU RAID, right?
No, from
No, the FPGA,
from the
sorry.
FPGA side.
Yeah, that's correct.
So you don't have a preamble which is BPSK modulated for...
No. Straightforward with the OQPSK, and that's it.
Yeah, have in mind that afterwards, because we face the same issues.
Okay.
Yeah, it is getting extremely complicated to switch from a BPSK only for the preamble or the, let's say, for the header, then to QPSK. So take care early.
Yeah, that's not implemented yet, but thank you very much for your notice.
Thank you.
Any other questions? Okay. Now, thank you very much. It was great. So, next one, have a lunch break. And we'll continue with then we will continue at 2:30 with the rest of the talks, and then is a session of lighting talks. If you are willing to do a lighting talk for a subject, you may do so too. There are slots available. See you in the next session.
I'll tell you what. Let me grab old fingers here. And beat the devil out of it. I'll tell you what. Let me grab old fingers here. Beat the devil out of it. 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 I'll tell you what. tell you what. Let me grab old Fanfish here. And beat the devil out of it. I'll tell you what. Let me grab old Fanfish here.
1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, εδώ θα μιλάω, θα πηγαίνουμε πέρα εδώ, ναι, γεια σας, it is me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Να το κλείσουμε και από το stream. 1, 2, 4, 4, 6, 7, 8, 9, 10. Σήμερα, παιδιά, θα συζητήσουμε για την επιστημονική φαινομενολογία και πώς αυτή συνδέεται με την πραγματικότητα. Για να μπείτε στο κλίμα του θέματος, θα σας κάνω την εξής απλή ερώτηση. Κατά πόσο πιστεύετε ότι αυτό που ζούμε τώρα είναι αληθινό, και τέλος πάντων, ποιος μας λέει ότι όλα αυτά δεν είναι απλά ένα όνειρο? Μου έστειλε μήνυμα κάποιος που λέει: ξέρεις τα νούμερά σου. 1, 2, 4, 4, 4, 5, 5, 6, 6, 6, 6. 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 4, 4, 4, 1, 2, 3. Μου αρέσει το toast, μου αρέσει το κάτι με πι, με πατάτα, το podium, μου αρέσει το podium, μου αρέσει το κρικέλια, υγιής δεν έχει. Το σοκάκια, σουτζουκάκια, καλαμάκια, σουβλάκια και άλλα. Σήμερα θα συζητήσουμε
Να. Κυριολεκτικά όμως. Okay, people. For our next session, with some really interesting tooling for your satellite missions, I will first call Kostas, a PhD from the University of Luxembourg, that will tell us all about how to actually lose all your hardware and do everything on testing with your laptop, accumulating your CubeSat. So here it is for Kostas, that actually assisted us in video and everything else.
Thank you, thank you, thank you. Thank you, Elkos, for the introduction. Oops, cable. Yeah, today we'll talk to you about emulation, and let's see if this works. I'm definitely prepared, okay. And I left my job at my AV booth to tell you about the problem that we have, which is testing your software, and I'm sure these are images most of you are familiar with when you want to test actual hardware. Here in the bottom you can see we have like a bunch of microcontrollers when I was still back on the CubeSat project with the people that presented earlier. And we actually, for testing, we actually had a complete hardware in the loop setup. So we had, you can see some microcontrollers that were connected to a server, and we used a GitLab runner to run continuous integration, continuous delivery, so that whenever we pushed a new commit, we automatically tested it on hardware. And you can see that you can see like 1,000 assertions passed. So everything was happy. You can actually look at the code. We have some links in the presentation, which is online. It's a very interesting project if you actually want to test something. So why am I not happy? Because this is hardware, and hardware has physical restrictions, because this is how nature works, I guess. And hardware comes with what we call constraints of physicality. So we have high effort. You need to know how to use hardware. You need to have people who know how to use it and have experience with it. Usually, I mean, it depends on where you are. It's harder to find hardware people than software people, for example. Cost is another consideration. Hardware is expensive. If you have like a cheap Nucleo board, it's nothing. But if you have like a $200, $1,000 radiation-tolerant board, then yeah, you're going to have issues. You're limited in how much hardware you have. Like we have needed to ship different microcontrollers to different people across the globe whenever we want to test something. And whenever you need to trace something, you need to get like an entire oscilloscope setup going. Software doesn't suffer from these problems. So with software, we can do anything. So in this presentation, we will see how we can use the QEMU emulator, QEMU, I don't know how you pronounce it, to interface and test your embedded software. So QEMU means quick emulator. Actually, the logo is an emu animal, which I just found out like 2 days ago. And it can emulate pretty much everything. So in this screenshot from Wikipedia, you can see that it emulates like a complete x86 system. But we are interested in the architectures that we are using, which are most likely ARM or RISC-V if you're one of the cool kids. And these people at QEMU, they have done a lot of work. That have like written a complete emulation of an ARM microprocessor. So in theory, we are done. It's already like used professionally, so presentation over. But I mean, it's not that easy, and it's not plug and play. And if you're dealing with hardware, you might remember that this is what the structure of a microcontroller looks like. And the processor is only one part, which is handled by QEMU, so trust me, it worked great. But then usually the microcontrollers that we get off the shelf, they have a lot of peripherals which are not standard, and there are thousands upon thousands of different combinations of peripherals, internal and external, that you can have in your microcontroller, in your subsystem, in your satellite. And when we want to emulate our software, we want to emulate this whole package. Otherwise, we will get what we see down there. So like I tried with the CubeSat software to emulate like in a default QEMU machine. Of course, you get an error immediately, like a hard fault exception. So QEMU provides this method, this technique of allowing us to write code for these external peripherals. And this is one method that we can use to emulate our software effectively. So again, I have the structure that I showed you before. On the right is the hardware, and on the left is the software and how its software component connects with the hardware. So we have some hardware abstraction libraries in the bottom, some device drivers in the top. If you've written software, you should be familiar with those terms. So what we want to do in the ideal case is that we take this onboard software and we use it as is, no modifications, and we connect it with QEMU. And we need to write all of these things in QEMU. We need to emulate. The architecture is done, but the peripherals most likely are not, so we need to go through the process of writing the code. And this is the hard method. There's another easy method, they call method number 3, is that you change your software so that your software does not assume the existence of those peripherals. So you add different code or different functions or different overrides in your software, and in this way you can avoid writing like proper emulation. So then QEMU only emulates the architecture, which we already have, and we are happy. There's also a middle ground between the two. So a hybrid solution, you can do one method for some peripherals, another method for the other, or a combination between the two. And this is what I prefer, because some peripherals you want to analyze in a lot of detail, some peripherals you do not want to analyze in a lot of detail, so this is the best middle ground for me. So what this looks like in practice, if you want method number 1, QEMU emulates everything, you really need to emulate everything, and everything is complicated. So if you want to get a temperature value, for example, you use memory mapped input-output, QEMU emulates the communication protocol, SPI I2C, then it emulates the device itself, so the device registers, how the device registers access the device internals, and then it returns the dummy value that it generates. If you don't want to go through that route and you let your software emulate everything, then you just have a software function and you override the temperature get function, for example, and you just return a number. Or you use a hybrid solution, so for example, in the bottom, same as method number 1, but you don't emulate some peripheral that you're not interested in, or you just get the actual value from QEMU instead of generating it yourself in the code. And I mean, in practice, this looks like this. So method number 1, QEMU emulates everything. You need to write the whole peripheral. Most likely, you will not be lucky. QEMU does have some peripherals on its own that are generic enough or might be applicable in your use case. The important stuff like UART, serial communication, maybe it's there. But if you want like specific temperature sensors, then good luck. So you most likely would need for this method to write it on your own. There are some examples already in the QEMU code base. There are some tutorials you can look. But in most cases, you might need to recompile QEMU itself. And you can see I have a list of functions that you might need to implement, like read the write from the memory mapped I/O, reset the state whenever the microcontroller resets, and so on. So this has a steep learning curve. You need some people to work on this, like have maybe a full-time job of actually creating peripherals and emulating peripherals. And it requires replication of all device functions. So if we're talking about a temperature sensor, everything is easy, we are happy. But if we're talking about like a subsystem or a communications transceiver, then yeah, good luck implementing like 150 pages of dataset. Method number 3, your software emulates everything. This is much easier. So if you have some abstraction in your software, you can just like implement a real sensor class that gets actual data or a fake sensor class that just returns 40 degrees. This is not completely representative, but it's a great way to get started if you want to just like test the actual business logic of your software. And yeah, remember, our end goal is to have something that's more convenient than hardware. So you need to look into the trade-off that your own team needs to take based on what kind of people you have available and what kind of needs and requirements you have. And the final technical thing is how you communicate between QEMU and yourself, basically, the user. And the user interface is not really that different compared to what you would use in actual hardware. So, for example, you can use like a UART serial connection. You can use sockets if you have like an Ethernet connection in there, UDP, TCP. You can use the GDB debugger. You can use semi-hosting for logging, or just like write a custom peripheral yourself. Because this is custom, it can be like very easy, just a few lines. So let's look at an example. This is again the example from CubeSat. So I took the code of the CubeSat project and I tried to see, can we emulate that thing under QEMU? And let's see if we can. So first thing, I modify the code a little bit. So we are using the hybrid method. I'm modifying a little bit of the code, and I'm implementing some of the peripherals. So here are like the extra code overrides I added, and then I added the build override in order to compile the code with them. And you see like a couple of peripherals that were necessary for it to execute, and some other functions as well. Most of the code is just empty because it's like initialize functions, and we don't need to initialize any hardware or clocks and so on. The only difficult thing are like the startup and linker files, and this must match the QEMU machine exactly. And this takes like 1 or 2 days to get working right, but once you do it, it's like solved, and it works forever. Then I wrote custom peripherals in Rust because I used another project that was written in Rust. So I just chose Rust for this. And you see we have like various peripherals, temperature sensors, GPIO for debugging, serial, and so on and so forth. And you can see also I have an example here. I mean, I don't care about the code really, but I want you to see like there are some transformations going on to convert a fake temperature value into a 16-bit that the sensor would produce as a register, so that you take this register value and decode it in your onboard software. And the reason for this is that a lot of bugs are in interfaces. I think most bugs I have seen in my life on CubeSat software are in interfaces. So this is why I do this, so that we can test the actual interface. And I mean, since we have a QEMU emulator running, we can also add like some functional tests, because why not? Like this is kind of a unit test. We generate a dummy temperature. We get the temperature from our microcontroller, and in the end, we test that the temperature that the microcontroller reads versus the actual temperature is close enough. And finally, we add some like command line arguments. We can add like GDB debugging, no display, semi-hosting to get some debugging output. We run it, and we see that it runs. We actually see debugging logs from the onboard computer. And you can also see in the end there is like an error, because I didn't write it very correctly, but please trust me, it works. So yeah, some common questions. Can we debug? Yes, we can debug. There is QEMU has a full-featured GDB client inside, and it works like no questions asked. The clock of the emulated system pretty much matches the clock of the host system. I haven't really tested it. I don't know. I don't think it's possible to change that easily. It can also run Linux. It also implements like some Raspberry Pi machines if you're running Raspberry Pi on your satellite. And is it worth all the time and investment that you have put into it? Well, for me, it is. And the reason is that, well, apart from the solutions to the problems of like physical constraints I mentioned before, we also have like some extra opportunities. So yeah, you can develop your code anywhere you want. You can do automated testing, but you can also do cool stuff like fault injection. So you can add faults in your microcontroller. You can add faults in your memories. You can add faults in your peripherals. Like you can do like the radiation hardened software testing in this way. And it's also much more observable, because through GDB and other methods, you have like full access to the memory of your peripherals and your device, and like the execution flow at any point in time without needing to pay anything or set up any extra hardware. Still, it's not straightforward, and I would say there is a lot of work to do if we want to make like this more accessible and usable in the everyday life of a CubeSat team. there is not really much information or tutorials available. There are not many devices, so if we have like a library of devices that people can use, like common temperature sensors, integrate them maybe into the Chemu code base, that would be nice. And then you would tell most people that, okay, emulate your software first, and then buy the hardware and test it out. And it's also nice to have like all this kind of analysis and so on tools. So my last slide, I have some code online that should be working, but this is like a project I'm still working on as part of the university. And unfortunately, with the university, we have some restrictions and constraints on what we are allowed to share before papers are published. I'm very angry about it. But yeah, there is already some code in there as a demonstration that uses Rust. And yeah, I'm also open for any questions. I'm not really an expert on this field, but I really wanted to get this point across of like, if you want to emulate, try doing it, maybe early in your project. You never know what you might find out. So yeah, thank you very much. Question? Yes. Yep.
Hi, thank you for the very interesting presentation. I think you only showed the method where you kind of replace the driver in your code. I would be actually very interested for the case where I have maybe some I2C device and I want to keep the software the same, but emulate it outside of QEMU, for example. And I think this is something that Renode does. I don't know if you've heard of this emulator, or maybe you can tell in general how you would emulate an I2C device without changing the software.
Which emulator did you mention?
It's called Renode, R-E Node.
I've heard of it, but that's all the information I know. I've just heard of it. I mean, in theory, you can also emulate in Chemu. And I know there are some devices already that use SPI or R2C, and the reason is that in like typical x86 systems, you already have those devices. For me, the way that I did this is that I implemented everything manually, so that I have a higher degree of control, so that I can inject faults in the protocols if I want to. And this is something that you can definitely do, because on the other end, the emulator end, you just have software. You just have something Turing complete, so in theory, you can do anything you want. Which means that you might need to implement the whole I2C SPI stack, and it's like part of the previous slide that I showed that we don't have a framework for this. I need to look into Renode. This is, this was something I needed to do, and thank you for letting me know.
+1 for Renode. It's worth the investment to try it. Yeah. Another question. So, do you use any kind of RTOS?
Pre-RTOS in the experiments I did.
And in Chemu, do you have any kind of extra, let's say, debugging tools regarding the stack usage for each task? Are those handles available on Chemu or not?
So this is not something I've tested. I know Chemu is compatible with Valgrind. I also know that some of the tools that are already available for hardware, like I don't remember if C-Lion has an RTOS like task or processor list. Because this goes through GDB, it also should work with Chemu, but I have not tested it directly. In any case, because operating systems are do not really rely on hardware apart from like a few interrupts and system calls and things like that. I don't think it's going to be like, I don't think there's going to be any roadblocks with whatever already works in hardware. But I'm not familiar with any like specific tools except Valgrind, and I have not used it.
Because, you know, most common problems in RTOS are stack overflows.
Yeah.
So it would be very cool to see if there is any kind of extra debugging tools there to spot them easily. And
yeah, I'm not familiar with any, so this is why I did my last bullet point there. Yeah, I think that's it. So thank you very, very much.
Okay. So our next speaker will be Jose. He's working for TU Berlin. Jose has experience in computer science and electronics. He's been part of the team of the Nano Formation Flight mission. And now he's working to get the lessons from security to the space industry. And he's willing to work on changing a little bit the paradigm of security in space. Let's hear him out.
So thank you very much, Elkas, for the very wonderful introduction, very kind. Yeah, so I think this presentation goes really well with what I talked about yesterday, and I think I accomplished my goal because some of you were actually quite concerned to find out that it's so easy to hack satellites somehow. And yeah, today I will present what we are trying to do to make it easy for everybody actually to make secure space applications. And yeah, our approach to do this is called Raccoon OS. It is a free open source operating system for secure space applications. Okay, but what is that exactly? So it's a few parts actually. It's a Linux distribution based on Yocto. We think that this makes it a lot easier for developers to write applications taking advantage of all of the existing software that we have for Linux, and also take advantage of the security mechanisms in Linux, like users, memory isolation, file permissions, and so on. The next thing that we add is a set of user space libraries and applications written in Rust. And I will show you what that looks like during the presentation. We also have a GNU radio-based ground station packet transceiver and a YAML mission control. So you can find all of this in the CubeSat repository that I linked here. This is basically a complete example of all of the software needed to run a space mission, and we are proud to license it with the GPL version 3. So who are we? Who's developing Raccoon OS? Actually, I come from the Technical University of Berlin, the chair of space technology, and we have a lot of experience, 30 years of experience with satellites. And we have partnered with other institutions, some startups that build hardware for satellites, Quantum Galactics, also the University of Bochum, and CISPA, which is a research institution focusing on security. So together we can kind of combine our experience in software and security. A little bit about the chair of space technology. So this slide we have to keep updating because we're constantly launching satellites, and this is actually only part of our research. But yeah, the NanoFIF satellites are what Elkas mentioned here, the mission that I worked on before. CubeSat is the mission that I will talk about later today, and various other missions testing communications, new technologies for space exploration, and so on. So, what is the reason why we're developing Raccoon OS? I think I tried to justify this yesterday with trying to explain how easy it is to hack satellites, but also some of our colleagues from CISPA and the Ruhr-Universität Bochum wrote a key paper in this field where they looked at the software from different satellite flight software and systematically analyzed the security vulnerabilities that you find and why they exist in a way. So maybe this should not be very surprising for you, but in many cases, simply there's no security mechanism at all, so that's already a big problem. And since these systems are typically implemented in C and C++, you have buffer overflows and all sorts of common mistakes that can lead an attacker to take over the satellite. And why do we not use standards for this, or why it's not as common? Yeah, it's also an experience that we make that CCSDS protocols are very difficult to understand. They're like hundreds of pages of PDFs, and you need to either find somebody that already uses it and tells you how to do it, or spend a lot of time trying to figure out for yourself. And also, space engineers, especially in new space, think of security last. And we're trying to change that by making an operating system that thinks about security from the beginning. So we looked at the existing operating systems out there. RODOS is a very common project used in German satellites. There's also the NanoSat Mission Operations Framework used in OPSAT by the European Space Agency, CFS from NASA, and F+. So we can see that there's not really a lot of security considerations. CFS and F' include CryptoLib, which is an implementation of the Space Data Link Security Protocol. That's already a great start, but apart from the NanoSat Mission Operations Framework, they are not written in memory-safe programming languages. And so, yeah, this is kind of why we decided to make RaccoonOS. In terms of security, we take advantage of all of the research that has been done for terrestrial computing in the last 40 years. So it's not that we have this today, but it is our intention to implement secure boot, file system verification, middleware authentication and encryption, so that even if one of your applications on the satellite is compromised, it does not necessarily mean that you can use any function of the satellite. And more importantly, the SDLS, the Space Data Link Security Protocol, and we have made some very good progress with this that I'll talk about in a second. So also an important, let's say, philosophy or approach for us is to use as much standard space protocols as possible. Here we can see a little bit of our progress with these protocols. So the Space Data Link Protocol is the basis that tells you how the frames are made, and some protocols for retransmitting the frames if they're not received, and so forward error correction. And also the packet utilization standard, which actually we took from a CubeSat, so we learned a lot from the implementation of at least the request verification service there. We still have a lot of work to do. We're also working with the YAMS team to implement the functionality that is missing in YAMS to be able to support these services. Okay. Also maybe an important feature of RaccoonOS is that it's all of the applications that we build ourselves are written in Rust. So with this, we already get a base level of security in the sense that we can be pretty confident that we will not have memory corruption vulnerabilities. Also, a feature that I would like to mention is differential updates. So when we're dealing with the Linux system, we cannot just send the whole binary, the whole file system image to update the system. We use a process called differential updates. So the way that this works is you take the version 1 of your software, you compare it with version 2, and you only upload the parts that have changed. And we can do this automatically, and we have basically immutable versioned file system, so we always know what is currently on the satellite. And this is already implemented in our Yocto distribution. Another key part of the operating system is the middleware that we use. So if you are familiar with ROS2 or kind of robotic applications, you know that there's this kind of topic system where you can publish and subscribe. And it's a very easy way that we found space engineers understand intuitively how to communicate between applications with this kind of topic system. And we chose Zeno as our middleware because, well, okay, it is written in Rust, it is compatible with ROS2, and there's also support for the typical programming languages that you might want to use. So a user can write your applications in Python, C++, or any other language. And in the CybeSat example, we already use Python for some parts of the satellite software. Yeah, I will not talk too much about the rest of the features because I want to show you a demo of the most exciting feature that we're presenting today. But first, I would like to say, okay, has RaccoonOS been used in space already? And yeah, the answer is yes. The first satellite that we launched with RaccoonOS was actually a commercial mission where the payload was a packet receiver and transmitter, APRS payload. And here we have a nice waterfall from SatNox that confirms that, yeah, the satellite is well. And yeah, the next one will be CybeSat. So This is actually a fun mission in the sense that there's no funding for this mission at all. So we won a competition from the German Space Agency to launch the satellite, and that's it. We don't have any funding for the hardware, the operations, ground station, anything like that. We just get the launch. Nonetheless, we do have some interesting payloads on board. The main scientific payload is a new type of solar cell called perovskite solar cells. You can ask me later what benefits these have, but maybe most relevant to this workshop is CubeSat will fly the first demonstration of a fully open source space data link security stack on board and on the ground. So that's what I will show you in a second. And yeah, I just want to show you also some pictures of what CubeSat looks like. On the left side, you can see the perovskite solar cells. And on the right, it's a plate inside of the satellite where we signed. It's a nice tradition that we have at the university. Okay, great. So now I want to show you what it looks like to write a very simple application using our framework. So this is the mission database definition of a boot service. So it will have two commands: get boot counter and reset boot counter, and it has one telemetry frame, get boot counter response. So this is how you tell YAMS. This is the data format for the command and telemetry. And this is what it looks like in the Rust code. So we have some macros that you can use to describe your commands and telemetry. You specify in this case the commands have no arguments, but we can see that the telemetry has it's a struct with one entry, 16 bits on the wire. And then this is kind of the implementation of the service. You implement a function called handleTC, where you get the parsed command based on the data structures that I just showed you, and then you decide what to do. You can either handle it with a telemetry response or simply return true or false, and this will then be displayed in YAMS. And now let me move over to the demonstration. So what I want to show you is, okay, one second, let me move this over. What I want to show you is the encryption feature. And I was thinking, how can you possibly show encryption? You don't see encryption. And my idea is to send the command multiple times, and we will see that the data is completely random. So what I have here is, okay, I'm running the link application here, and I am running the boot application. I am also running Wireshark, so we can see the messages that the software sends to the ground station, as you would if you were listening to our downlink, for example, on SatNox. And okay, let me reset this. So first I will send a command to get the current boot counter. Okay, and we see that it's 1. I will restart this application many times so that the number goes up. Okay, so we've restarted it a few times. I will request the boot counter again. And okay, we can see that the boot counter is 9. Now I can reset the boot counter. Okay, I can request it again, and it's 1. Okay, so if we didn't have encryption, you would think that these commands would look pretty much the same on the wire. But what we have here on Wireshark, okay, we have 4 packets, and I will just quickly go through them, and basically we can see that the header is more or less the same, but the payload data of this packet is completely random. So, okay, you have to trust me that this is encrypted, but you can pretty much get an idea that there's no pattern in the payload data of these commands. So this is the demo of SDLS, and we will continue with the presentation. One moment here. So here we go. Yes. Okay, and also just briefly, after CubeSat, the next satellite that we will launch with Raccoon OS is called CISPASat. This is the first satellite from our colleagues at the CISPA Research Center, and they want to do some cybersecurity research that I will not talk too much about. Yeah, and just to summarize, we want to create an operating system that is open source and standards-based to take advantage of all of the security features that we have on terrestrial computing. We want to make it a lot easier to update Linux systems with differential updates, and we have many more features that we're planning. And this is a little bit of the launch schedule. As I mentioned yesterday, we are also founding a non-profit organization to hold the intellectual property and hopefully get funding to continue developing it beyond the Raccoon project at the university. And we are definitely looking for people that find this interesting, want to help us, want to try the software, write documentation if you're so kind. That would help us a lot. Here are some links. Also our Matrix channel that you're all very encouraged to join. We have meetings every 2 weeks where we go over the progress of our different missions and software development activities. And also just finally, I want to highlight some of the contributions that we've made to the open source ecosystem dealing with space libraries. This is not exhaustive, but just our little way to say thank you for all of the great help that we've had from the open source community. And yeah, thank you. Are there any questions?
For your secure boot implementation, considering that you're an open source project or, well, some form of foundation eventually, the usual issue that projects have that are somehow open source is that to actually get the key signing material for your trust zone and for your secure zone signed in the first place, most institutions, including the Linux Foundation, can't get that done. I mean, for Linux, I think it's Microsoft that does the signing, which is like creepy. But how do you hope to do that, assuming you actually can? I'm curious.
At least for the processors that we've looked at, they are system and modules meant to be used by an end user that installs their own signing keys. So this would have to be part of the initialization process. That would be part of somehow a way to install your own keys, trust the bootloader, and then from then on you have the root of trust. It would have to be user installed in each case. It's not something that we would have the Raccoon OS signing key and everybody trusts it. Every user installs their own.
What about the SDLS packet processor of YAMS? It's already mainline. It's a custom one that you integrate in YAMS.
Yeah. Okay. So I skipped over this really quick actually, but I highlighted in bold because I think it's an important thing to say is that our colleagues from CISPA actually funded the YAMS developers to make an open source implementation of YAMS, of SDLS in YAMS. This is already in the public repository. It is not released yet, but if you compile YAMS from source as of today, you do have SDLS support, and you can see in our CubeSat repository how to configure it basically. So this is already public.
Mainline on the on the YAMS code base.
Yes, exactly.
Great, thanks.
Hello, thank you for the presentation. A follow-up question in regards to certificates. So, given the choice between a user that has forgotten to update their certificates, or has improperly configured their expiry, would the OS favor recoverability or security? Meaning that would you rather have a mechanism that blocks everything and causes the communications to fail, or would you allow some sort of special case factor to recover?
Yeah, so this is also basically the main concern that satellite operators have when deploying any form of encryption. What if I lose my keys? Do I lose access to my satellite? I think this is kind of still an open question. There are some ideas for how to deal with this. One such idea is to say, if I've not received any encrypted messages in the last 7 days, I fall back into some kind of safe mode where I accept unencrypted commands. Of course, this is not necessarily the best idea from the security perspective. You can just do a denial of service attack against your uplink frequency, and then now you have unencrypted access to the satellite. This, yeah, as I say, I think it's kind of an area of research. How can we possibly make it secure and fault tolerant? I do have some ideas, but I'm not ready to share them yet. It's an open discussion, basically, so you are very welcome to join our Matrix chat and discuss it.
Can you put the QR code on your piece again?
Yes, here you go. Okay, no other questions, so thank you very much.
Next in line, and last proper talk for the day at least. Next are lightning talks. Is Libs 3. The presenter is Osman Kiros Jimenez. He's working for the German Aerospace Center, DLR, and he will tell us all about parameter management software.
Thank you. Thank you for the introduction and being here. I want to share you about this little project I have been developing like in the last 2 years, more or less. So yeah, I work at DLR. I do software development for optical terminals. And so flight software, and it's great that in the last presentation the colleague mentioned about the flight software frameworks, because I will start talking about exactly this for the introduction about parameter management systems. Here, okay, so talking about flight software frameworks and how do you write software for satellites. Of course, you can write the software of your satellite however you want, but it's very common that some services or some services are you can find them in basically all satellites. One of these services, it's the parameter management system, which if you haven't heard about that, it's basically like a key value data structure or service. And you can basically store any type of data related with a key that usually is a number. Some examples of these frameworks that have parameter management system is, for example, F prime, which is quite popular. Also, CFS from NASA is also quite popular. DLR also has this Outpost framework, also has a parameter management system, but it's not that popular. And if you know also about the ECSS standard, they define also how should a parameter management system work, or at least what are the functions it should provide. And so in the last years working at DLR, I have had the opportunity to work with some parameter management systems from, let's say, proprietary vendors. And I have found some limitation or drawbacks that made me think, well, maybe here there is some space for improvement. And I think the biggest one is that they are not user-friendly at all. First, they use unique numbers to numbers to identify the parameters. So you have to remember exactly the numbers that you want to find, to set, to get. Also, most of the time, they have just like a binary interface, so you have to be converting the values by hand. And at least for colleagues that are not into software, it becomes quite tricky and complicated to use the tools or whatever the software framework provides. Also, they are not flexible at all. Like once you define all your parameters and how will you transfer them into the telemetry and telecommands, it's like frozen, so you compile and that's it. There's no way to change when it's in orbit, the satellite. You'll have to do a software update, basically. And sometimes, let's say if you just want to, if you find out in your telemetry, you don't want to receive this specific parameter because it's not that useful. You find out you want to change or add other parameters. I think it's too expensive to do a software update for such a simple thing. So yes, what I'm proposing here, first, better to use readable names that you can remember, that make sense, instead of just numbers. Yeah, also the parameters should be independent accessible so that you can set or get exactly one and you don't have to request, let's say, the whole memory of the satellite or a whole telemetry frame just if you want to get one parameter or, yeah, exactly. Yeah, and this should work not only for telemetry, but also for telecommands. And yeah, last but not least, I also took some inspiration from the space system model from the ECSS standards, where they make this analogy or they provide this way of explaining space systems, just like a hierarchical structure, which I think is very convenient. It's a very intuitive way of explaining and understanding space systems, which are very complex, just as you have your top-level system that's divided in smaller subsystems, so on and so forth, until you arrive to the smallest units, which are the parameters. I think this is a great way to share information between people on how a complex systems work, and I think the software should also reflect this this concept. So like the software should reflect this hierarchically nature of the systems, because these help different people to understand the same system. So that's basically what I did. I took these different ideas and I started implementing my own parameter management system using trees. So I have the, let's say, the node object. I call it system, and it has a name. That's everything. And these can have other subsystems, which are the child nodes. And then you have the leaves, which are the parameters, and they have basically, you have to assign, which is the parent system, a name, and the value, sorry, the data type, and you can put a default value to those parameters. You can have basically all data types supported by C++, and you can also have vector parameters. And this is how you build your hierarchy. So this is how you start building your tree. You can think about like a file system where you have like directories, and you double click, and there are more directories. You double click until you get to do your files. Those files are like the parameters. And I have also built like simple command line interface to navigate across this tree, which is very convenient. You don't have to look into a huge list of parameters. You can just navigate as you navigate files and folders in your computer. And I think this is also very convenient for people that is not software, the people that doesn't work just in software. How do you then use your parameters in your software? You just have two main functions, set and get, and that's everything, very easy. Other benefit of using trees is that searching in a tree is quite fast. I mean, at least faster than looking into iterating over a list. And okay, and then how can then I implement the telemetry and the telecommands with those parameters in the tree? Then I introduced what I call the groups, which is basically you have reference to each one of the parameters that you want to put, let's say, into a telemetry frame. You can have several groups. You can also leave space at the end of the group if later you want to add more. And with those groups, then you can pass them to serializers to serialize them either binary or comma separ value or TOML or YAML or JSON or whatever. I'm working on implementing those different formats for serialization, deserialization, which is very convenient. So yes, other few cool features of the library are the callbacks. Basically, for example, for checking values that you don't want a parameter to go out of this value every time you set it, you can use callbacks to check. Or if you want to trigger things, let's say every time you set this voltage parameter to a specific value and you want to then control an actuator with this, you can use callbacks for that. You have also search functions, conversions to string from string for the command line interfaces, or if you want to store in files. And as I said, also serialization, deserialization to different formats. Okay. This whole thing started just at the C++ library, but across the time it started to grow a little bit, and then having for the projects I work, which are relatively simple, it's just a payload, we already have between 500 to 1,000 parameters across different subsystems, and then how can we work more easily with these different people working on this data structure. And then I implemented also a transpiler Python implementation that I will explain a bit. So I create this model in YAML, and then in the YAML, basically you specify the same data structure, but in a more human-friendly way, just like this. Text that I guess is quite easy to understand. So the same story, you have your systems, parameters, and so on. You can divide the tree in different files. So like, for example, the people working on the EPS have a file, the people working on the ADCS have another file, so you don't have conflicts there. Also, you can specify the groups in these files, and this is very convenient because sometimes before, if you implement the interfaces between the systems and then someone change one interface and didn't tell the other person, it will break everything. With this, we have the model, the S3 model in one repository, and every time someone changes one interface, push the change, then every time I will compile again, let's say in other node or whatever, I update the repository and I have already the interface updated. I don't have to do everything manual. Also on the electronic support equipment in the ground stations that will recover the telemetry and plot. We just do an update of the repository. I already have that everything updated and it won't break the things. Yes, this is basically what I just explained. We use the S3 model for the ground stations, for the code, and also for documentation. It's quite useful also for generating the ICDs for external partners or users. We specify which are the parameters. All this can be generated with a transpiler. Then also a very simple Python implementation. The Python implementation is not as advanced or a feature-full as the C++ implementation, but basically we use it for testing. So like set get parameters, quite like black box testing, and we have like UDP and CSP getaways for communicating with the nodes running the actual firmware. Also working on a command line interface for this like useful exploration of the tree, so that people can use it like if it were any file system. Yeah, other things that this is not yet implemented. This is on development, but for example, I thought like for example doing queries would be quite cool to have if I want to get like all the parameters with a specific name or specific value. And yes, that's basically it. Some things that I have also in the horizon that I want to implement is access control, which parameters should be protected with different levels of protection. Also the trace safety model, I haven't enforced any trace safety model until now. Is up to the user. And yeah, other ideas I have, for example, do it POS compliant, so it will be easier to use on any POS if you need things like this. Yeah, that's it. Any feedback will be really appreciated. I have to important disclaimer. It's in development, so many things of the library could break if you, could change in the near future. There is no like version 1 still, it's still in version 0. It's released as MIT, so it's in the, I forgot to put the link here, but I updated the presentation, so if you download the latest version, the link should be there. Yeah, that's it. Thank you.
Okay. Any questions? Yeah.
Hi. So very interesting, especially to easily access all of the parameters of a system. And can it also just replace commands at all? Like you don't use telecommands anymore, you just change parameters and change modes. This makes the system do what you want?
Yeah, basically we have reduced a lot the number of parameters because mostly we use set and get parameter, and that's it.
You mean the number of commands?
Sorry?
You mean you've reduced the number of commands?
Yes, sorry, the number of commands, yeah. With set and get, you can do basically everything. Because you set, let's say, mode of operation, and that triggers a lot of things. And yeah.
Okay, thank you.
So yeah, I wanted to say sorry also, but we haven't get completely of some important commands, like for example, if you want to switch to specific mode, but under the hood, what it does is just like a shortcut to say, set this set of parameters to a specific value.
Do you have something like an atomic update of all parameters, so that if you say, okay, I want to switch mode to ADCS pointing and I want to use these target parameters, try to access the parameters before you've completed changing the mode or something like this? You have like an atomic update of multiple parameters?
No, that's not implemented. Also not like rolling back, not possible. What you could do is like having different versions of the parameters in files, and then if you want to do a rollback, you load another file, and the file can have just specific subsets. It doesn't have to be the whole tree. That's something you could do until now, yeah.
Okay,
thank you for the question.
Hi, thank you for the presentation. You mentioned serialization and deserialization. Do you foresee any scenarios where you have data in it that you cannot serialize or deserialize for any reason? Or do you have a safety mechanism for safe loading and unloading of data?
What do you mean? I mean, in which cases could you not serialize or deserialize? You say if the data is broken?
Maybe that's the case, or if you can allow arbitrary storage of information, something tries to get deserialized, it's not implemented correctly, and it breaks. What would then happen if you allow bit streams or string representations? That would not normally be the case, but sometimes if you allow definitions of arbitrary data, it can happen with poor implementations of the representation.
Okay, thanks for the question. There are, I think, several things which some are considered by the library, some are not considered by the library. For example, if you get a binary stream of data and you want to deserialize that and the data is corrupted, that's not considered by the library. It should consider, let's say, by the transport protocol of whatever is moving the data. The library assume what you give in the buffer is correct. So it's up to the user to make sure it's correct or not.
I'm curious why, as a parameter management system, you want to impose or enforce thread safety. I mean, this is something you talked about now at the very end quickly, but can you shed light on why you would want to do that?
It's a very good question. Yes, until now, I don't enforce any trade safety, but I guess it will be, I don't know, convenient, or I don't know, make sure people won't use the library in a bad way, and so that they will, I don't know, shoot themselves in the foot. So it's something still to be decided. If, yeah.
I understand that part, but still, like, can you explain why you're considering that in your context? I mean, usually thread safety is something that you consider for deep embedded OS development. If you write a kernel, a real-time OS, something like that, or below that level, if you're writing a ton of assembly. In your case, you're a library, so just trying to understand.
Because this is how will you will store the data for your firmware, for your flight software, and that data will be used in critical parts, like, I don't know, controlling the actuators, controlling your satellite. And if someone uses it incorrectly and you start doing weird things between threads, then things can go very wrong, right? So yeah, it's...
You're essentially worried about misuse.
Exactly.
Hardware users that don't really know how to interface with you.
Exactly, yeah.
Strong recommendation. Usually we leave that to the user. If they misuse our libraries or our code, you can give them guidance, you can tell them don't do this ever or else. Try not to prevent people from doing something that is strictly based on their abuse or misuse of your software. You can try to prevent them, but then they'll just patch that out, or if they still want that, or they'll stumble across it and they won't know how to deal with that. It's try to not step out of what don't try to be too defensive as a library.
Yeah, okay.
Maybe that helps.
Thanks for the recommendation. Yeah.
So my question actually is then from Christians. Do you do it maybe because you use tree structure to store the data and then you rebalance, or you do something in the background?
Oh.
And if so, sorry.
I did not get the last part, sorry.
So you're using a tree structure to store the data, right? So thread safety in that case would be meaningful if you need to rebalance the tree for whatever reason. And if so, have you considered tree structures that do not need rebalancing or are more tolerant to becoming unbalanced?
No, I'm not. No, I mean the trees are static. You cannot do rebalance. I mean for the data itself of the parameters, because you might you might use them for data sharing between threads, but that will be like sharing any other variable, which you should protect if you want to use it for that. No, yeah.
Okay, interesting. Clap for Oman.
Thank you.
This finishes up our session. Next thing, we have a break, and then we'll continue our lighting talks. Keep in mind that if you want to do an impromptu lighting talk, go to the registration office and sign up yourselves. It's doable if you feel like it, as long as it's about space and open source, of course. Thank you. See you at 4.
Listen a minute to Kitty. sight, out of mind.
Anna? Okay, people. We have a couple of lightning talks. The first one is by Tristan. Remember correctly? Yeah. Tristan is from Decent Space. He's going to be talking about a framework of blockchain verified ground infrastructure, which is kind of provocative for me because can we really put greed into building open source ground infrastructure? Well, let's see his views.
Thank you very much. So yes, I have a nice timer here, perfect. So yeah, my name is Tristan. So yeah, I have a company we're called Decent Space. I'm also a graduate student at TU Berlin. And yeah, I'd like to talk a little bit about potential use cases for blockchain, especially as they might apply and be beneficial for open source systems. Yeah, just like a quick, well, we'll just skip to the key challenges, that's fine. But quick overview is there's been some research. I would definitely encourage people, if they're interested, ESA did a report with GMV. They did a 2-year report between 2022 and 2024. It's published. If you're a resident of Europe, you can get access to that. And they outlined a lot of the key places where distributed ledger technology, more specifically blockchain, can play a part in being useful. And so some of these key areas are and I'm focused specifically on the ground side, and we'll do an analysis of some existing projects and how they apply it and where it might be applicable. But in some of these key areas, we have areas like compliance, security, automation, and access. These are some of the very key areas that it could be impactful and beneficial. There's several potential application areas, specifically ground station networking validation, compliance through activity validation, and spectrum management. So the first fundamental principle I just really want to get into so we can understand this is consensus mechanisms. And so these are mechanisms where you have to, like really, it's kind of like a deeply epistemological thing. We have to be able to figure out what exactly is true about the reality around us. You can do that through utilizing peer-to-peer systems, and specifically one of the most interesting use cases for me is when you're using IoT devices as those systems that are generating a valid proof or something that's validating a event. And so essentially we have a few key components. So we're looking at some type of cryptographic signature that's going to attest to the truth of some event. We want to have some degree of Byzantine fault tolerance, so this is going to be ensuring the reliability of a network of nodes to prevent malicious nodes from entering into the network. And we want to focus on how we can distributed verify specific points of failure or manipulation in the network. I think that there is a need for truth. So decentralized networks, they handle this through using these decentralized networks of nodes, which are these devices that are going to be creating some trust between an unknown number of peers. There's going to be, you want to be seeking some type of robust, which means you have a higher volume of nodes ideally that are reliable. You want to verify reality and prevent manipulation. Centralized networks do handle these challenges, and sometimes they are the better option, to be clear. They use it through a centralized trusted authority, through legal contracts, auditing, system security, et cetera. I have this visualization where we're looking at different types of architectures. Federated doesn't necessarily mean it has to be blockchain, but something where you do have like a pretty large network of nodes that are acting independently. And then you might have a single provider or a multi-provider architecture, and they work good in different situations depending on what you're looking to get out of it. Some existing companies that are working on this, so like Helium, they're probably the most best known. They're they're part of what's known as decentralized physical infrastructure networks. They're one of the first big ones. They started as a LoRa network, providing basically LoRaWAN coverage. Now they also do 5G. People usually, you will set up a node, a hotspot essentially, you're providing internet, and you get rewards for providing that internet. You have various nodes in the network that are validating that you are also indeed providing the coverage that you say you are, and you get rewarded for doing so. GeoNet, they provide a verified GPS or a GNSS location for people who need hyper-accurate data. They're also a successful, profitable company that has implemented, they have tens of thousands of nodes globally that are focused on providing this. A really interesting new project is called SpaceCoin. SpaceCoin, they are focused on this with regards to satellites. They've put up one satellite, they're putting up several satellites in the next year, and they're looking to have basically community involvement and putting up satellites and providing a decentralized Starlink where you could be using it as a secondary payload and getting rewarded for providing coverage. And then another really interesting one, I think, in terms of networking, there is this one called Witness Change. They came up with a proof of backhaul, which I think is really interesting if you want to develop a trust in the mechanism that is transmitting data to the end user and being able to validate that they are indeed providing the service at the speed that they say they are. And then we're focusing on, it's experimental right now, but how we can prove compliance in systems. So yeah, I think that what's really important here is that people participate, people give feedback, people are skeptical, but there's a lot of value to this, especially in regards to if you need to build a community and incentivize development on the community of IoT or in a distributed network of IoT nodes, it can be a powerful way to do that. So thank you.
Lightning talks usually don't have questions, but since we have some time, I'm always standing in front of that speaker. Anyone has any question? Okay, just one, man.
Hi, thank you for the speech. So, quick question. You mentioned distributed evidence of something happening or something holding true. Blockchain usually has a priority, let's say, addition to the chain where you have the first one adding something and the most signing that addition acting as proof. How do you resolve having multiple proofs for an event given that? Do you modify the way blockchain works or something else?
I was going to ask a clarifying question, but it's okay. So if I'm misrepresenting this, we can continue the conversation as well. But the way that I understand it is that are you asking if there's conflicting nodes that are saying two different truths, essentially, and how do you resolve that? Is that the question, or? Mm-hmm.
We say that, okay, I don't just want to have the first one who reports it invalidated. I want all five of them in the blockchain.
You can
the addition of all five sources of truth, let's say. Do you use a modified type of blockchain, or do you approach it differently?
So they would all be able to record a specific event on the chain, and then you would have the peer nodes validate that event and record. Yeah, they would all be added and validated, yeah. Correct. Yeah, this would be a different approach, yeah.
Okay, thanks, Tristan. Next talk will be Simon Bourria. I'm not sure I'm pronouncing it correctly. Interestingly, it's an open source wrapper for Basilisk simulations. And, let us first prepare our thing.
What would you prefer?
Okay.
Okay. So my name is Simon. I'm working at the ISAE Super Lab in Toulouse as a postdoc, and I'm also working as an engineer for AICO, which is a company based in Torino, in Italy. And AICO, they work in software embedded on satellite, and mainly artificial intelligence software, and they want to have autonomous behaviors for satellites. So this is where this topic comes from. So I wanted to do a lightning talk because it's a work in progress and we are just starting. So basically, the idea is to have your feedbacks and take your inputs. So the context for this study was the need from AICO to test their software on satellites in astrodynamic frameworks, and especially the softwares, as I said, to obtain an autonomous behaviors for the satellites. So they're mainly working on station keeping algorithms and collision avoidance algorithms. So they benchmarked the existing frameworks, and while most of them are largely good enough to perform the simulations they wanted to perform, they were losing time and efficiency when changing scenarios, for instance, or when changing the languages of the algorithm, adding objects, plugging machine learning, and stuff like this. So, and mostly also because a lot of people that were using the framework were people that don't necessarily have the background to dive into the astrodynamics, but still need to modify the scenarios or send information. So the need came for a modular framework, so really designed as a plug-and-play framework to increase the amount of testing for the company, and that could also be made and be used by non-experts. So we decided to work on a wrapper of an already existing framework, and this framework is Basilisk. So just as a reminder, Basilisk is an open source astrodynamic framework that has been created by Boulder, the University of Colorado Boulder. And it was our choice for several reasons. We already worked on OREKit. We tried several frameworks, but this one has a really modular architecture, so each physical subsystem is a Lego block, and the block communicates between them with a specific messaging architecture. And this was interesting for us to build upon. So we decided to start with Basilisk and work with Basilisk. Very quickly, the workflow of Gecko right now, as we have started it. So you start by configuring your scenario by putting a JSON file or by modifying a Gecko class. Usually we do both. We use the JSON files to have the initial parameters, so the orbital parameters of the satellite, the size of your satellite, and so on. And then the Gecko class is here to configure your scenario. So you modify already existing functions to obtain the scenario that we want. We tested it for the station keeping algorithm of the company. So basically we had several parameters, and the satellite was supposed to behave in a certain way based on the reference orbit and when it was too far from a reference orbit. And then the simulation just runs by loading the configuration parameters that are the JSON parameters, and by then running the scenario that you have defined. So the idea was really to have the lightest and easiest way of building the scenarios, and then just run the Gecko wrapper on the scenario. Then we have, we can plot a lot of things, but as I said, it's a work in progress. So we can have ground tracks. Here it's a scenario where the satellite could only maneuver above land. That was just to try an example. So that's why the green is only above land. You can plot it in 3 dimensions too, and there are a lot of things you can plot quite easily also with already defined functions. These are, for instance, the position and velocity deviations compared to the reference orbits that you give to the satellite. So we simulated the mission control center, the ground stations, the satellites. Everything below is Basilisk, but you don't have to know anything about Basilisk to understand how Gecko is working and to do and perform a lot of simulations. A quick thing that I wanted to mention is we are currently working on conjunction data messages. So for those that are familiar with CDMs, it's quite difficult to get really good CDMs or huge databases of CDMs. But it's really interesting in the case of, for instance, the collision avoidance algorithms. It's really interesting to have the simulator be able to send fake CDMs to the satellites to see if the satellite can automatically choose to maneuver or not. So we wanted to generate CDMs, and we are currently working on this algorithm to generate the CDMs. It's using two things to create this, to generate these CDMs. The first thing is the database from ESA that has been used for, if I remember correctly, it was an artificial intelligence challenge that you can find online. And it's one of the only really huge CDM databases that you can find online. And we are also using a lot of conjunction events that we simulated using Gecko. So we run Gecko for a long time with a lot of debris and different satellites at different altitudes. And we record all the conjunction events. And this, combined with the ESA database, help us generate CDMs. But we are currently working on it. So that's it. Thank you very much. And as I said, it's really, the idea is really to discuss about it. So feel free to contact me, and let's keep in touch. Thank you.
So we do have time for one question, maybe? Or no questions, interesting. Thank you, Simon, it was interesting. Now, the next thing we have to do is the closing ceremony. Okay, it's not really, I'm not into, okay, I am, but I'm not into ceremonies a lot, so I need to share some thoughts, some ideas. Most importantly, I want to thank you for being here, for participating, for actively participating too. It was really important for me. It was great watching all these things, learning new stuff and getting new insights. As always, OSCW has been a real inspiration and has been also a great way to remember how we do stuff, revisit how we do stuff. And we have come to the conclusion that the open source CubeSat workshop is much more than just talking about CubeSats. So we start thinking about, should we still call it a CubeSat workshop? The answer is maybe not. Will still be open source? Absolutely. Will it still continue to be about space? For sure. We will only limit ourselves to CubeSats? No. We do build pocket cubes. Other people build optical systems. Other people build systems for light pollution. The space community has a lot of people and a lot of expertise and a lot of ideas around it. And we should use open source in all these sectors of the industry. So maybe in the future, OSCW will have a new name. Maybe you can suggest one. But still, it will be open for everybody to participate, to be in the physical place, always to have it accessible online for everybody. And I need again to thank Konstantinos for his valuable contributions. All my colleagues at LibreSpace Foundation that have actually worked night and day to have this event done. And to all of you for participating with your presentations and with your mere presence here. Thanks a lot. And last but not least, I know that you know that most of us are inspired by the vision of the LibreSpace Manifesto. And you're free to check it out at manifesto.libre.space. And if you consider it a good idea, sign it up. Thanks a lot.